Thank you for joining me today to hear about flat containers and to discuss some caveats of using these data structures. First of all, this talk is planned for like 45, 50 minutes. And if you have any kind of questions or comments, just raise your hand and ask. I guess we also have mic here, which is functioning. So if you need it, I probably can pass it for you. Yeah, okay. So first of all, a few words about myself. My name is Vitaly, and I've been doing software for quite a while, mostly in C++. Now I'm working at Remarkable. This is a Norwegian company, and we do this e-link like Notepad that provides very nice writing experience. So if you do a lot of notes and stuff, or working with some schemes, charts, or somehow visualizing your thoughts, that's very nice stuff to use, and we use it a lot at work. For today, first I want to give you some overview of existing containers and the containers that will be included into the standard library at the C++23. We want to look into some implementation details of those containers. Then I'm going to talk about some advantages and why we might want to use those containers in real production code and what kind of issues they can solve for us. Then we will look to some very artificial benchmarks, and I will tell you why basically you should benchmark everything yourself when you do real production code, taking into account all of this hardware, build flags, and so on. And then there will be only one slide of general recommendation, how you're going to use them or how you want to create those containers and so on. Yeah, let's get started. With a small overview of containers. Before C++23, we had only those three in the standard library. Then in C++23, we have things with underscore flat prefix. And somewhere in between, that's not the matter I want to talk in this particular time, should be Google upsell containers that based on B trees. That's kind of hybrid between of pure flat and spare tree structure. And now the short question for you, because flat containers are not kind of a new thing. So how many of you ever used flat containers from Boost, from other stuff? Oh, good. Cool. So to understand why they're actually flat and what kind of properties they utilize, we should... similarities. That slide I always forgot about. So all of those containers, they are associative containers with some difference because standard gives us a definition of what the associative container is, and arguably flat things are not fully associative according to this definition, but let's not talk about it. All of those containers, they require to have std-less operation to compare keys, and all of those provide logarithmic time for search, which is very good and fast. And we should start with stud_set to understand the core differences between those containers. So who knows what under the hood of stud_set? Okay, ish. Yeah, then we can talk about it a little bit because this is very good question for programming interview. We are not doing it in Remarkable, just in case. So under the hood is a tree. It's not just a tree, but it's a self-balancing binary search tree. I strongly believe that in most implementation, this red-black tree, not AVL or something else. So some fundamental properties of those tree helps us to provide good complexities for three major operations. And those properties are that this tree is kind of sorted. You may see that the root is in the middle, and all left nodes are either less or equal than the root, and all right subtrees are greater than the root. And that repeats for all subtrees. There are other fundamental properties, and I'm not going to talk about it, but basically, to keep it balanced, there should be the same count of black nodes, and each children of red nodes should be black, and so on. But yeah, it's not important for now. Another important property that what we can do with this tree is we can do in order tree traversal. The green dot here is where the traversal starts. It goes from the root to the leftmost subtree, then up this way. And if we just traverse it this way, we can get a sorted list of elements, which is a very good property, and we need to keep it in mind to understand flat containers better. And as I said before, that's just a tree, and this is very naive implementation of such a tree written by me. So here we have just a node for set. Then we can the same for left and right subtrees. We have a color, that just enumeration in this case, and we have a value. That's how it can be implemented. And from even this implementation, you can see that we're not storing just a value or key value pair instead of map, in case of map, but we are also storing sort of color. That doesn't matter, this color bit or just enumeration or something. And we also need to store pointers to two subtrees. That kind of create memory overhead that can be crucial in some cases. The fundamental properties of this tree that I described before, they guarantee us all three basic operations, complexity of log n, which is very good complexity in many cases. And if you do traversing of the values of this tree, they will be sorted in ascending order. So they just, when you traverse it, would be in order tree traversal. But now let's talk about flat set. So who knows what the under the hood of flat set? Good. And this is super simple. This is just a ascendingly sorted contiguous container of elements. It's sorted vector in many cases. So, and that's why you can see why it's flat. So we took a tree, we collapsed it, it's flattened now. Here I tried to visualize binary search on this container. So, and it is like when we're searching something in a tree, we're starting from the middle, then we, since we're searching for 0, we're checking, okay, not this element, then we go left, 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 until we find the 0 element. And that's why we can guarantee logarithmic time for search here. The possible implementation of this container could look this way. I guess it's copied from the standard, because all my implementations show here they're just not a reference implementation. It's very naive and simple implementations. The point is, if we look into the features per compilers, flat containers are not implemented in any. It just threatened this table. And this morning I checked, there are some pull requests, especially for Microsoft STL, which is open, but it's not merged yet. And there are some discussion, I guess. The first commit was done at 2nd of July or something like that. And now it's 50-something commits and very long discussion how to implement and merge flat containers. So, but get back to this stuff, to my implementation. What we have here now is key. We have comparator, and we have containers for storing keys. And from this, we can get that this is not like a container, but it's container adapter. And in this particular part, it's placed in the standard, so it's a container adapter. Here we have two members, one for container and one for comparing stuff. And there are some very important limitations for container and for iterators. So based on standard, we should have a sequential container that provides random access iterators for performing binary search efficiently. So it means that not all containers can be used here. It should be satisfied this particular requirement. Now let's talk about find operation and why it's also logarithmic. This code is quite simple, and we can assume that the underlying container is sorted because we're using only methods, and it helps us keep an invariant. So on this slide, in the code, I'm using lower bound, and the lower bound from ranges. It can be lower bound from standard library with containers and something. I guess I used ranges with v from my implementation, not super important. Lower bound takes a container, takes a key to search and a comparator, and it returns first element that either equal or greater than the key. So, and here we can check if element is completely not found, we return the iterator to the end, but here, if element is found, we return the element itself, and otherwise we return that of container. Strictly speaking, this is a binary search. So that's the complexity of it, it's logarithmic. Very cool, we're good here. But if we move to other operations, we move into insert operations, say. So in the insert operation, we also utilize lower bound here. We could implement insert in terms of find, but it wouldn't be that convenient in this case. And we can find an iterator, but here we should check if the key is the same. Based on standard, we should maintain uniqueness of keys. So I cannot insert. It's kind of stable insertion, if you will. So I cannot just replace elements. And in this case, I also should return an iterator to the element. Here I am cheating a little bit. I'm assuming my container has this operation to insert. So I'm having my iterator and the key to insert, and then returning what I inserted. That might potentially work for logarithmic time, but the problem here is that we need logarithmic time for lookup itself, but then say we want to insert something in the beginning of the container, and container does not prelocate any kind of space at the front part. So it means that we need to move all other elements, which gives us worst case performance is a linear for this operation. So, and another caveat, it's pretty much the same as for vector. So it can invalidate iterators. Why? Because we can shift elements, or we can completely relocate the entire chunk of the memory. Because that's how vector works. If capacity is not enough, that would allocate more with some factor and then move all elements into the new chunk of memory. You should keep this caveats in mind. And someone asked me before the talk, can you use those containers as a drop-in replacement for standard containers? Please don't do it, because some code can rely on the property of iterators and so on. You should be very careful when you decide to use something as a drop-in replacement. So no questions so far. We can go. The erase operation, and erase is implemented in terms of find. We just do find, but here on the one interesting thing that we need to check whether this iterator is valid or not, because that's requirements for erase, that iterator you want to erase shouldn't point to the end of the container, to the behind of container. And that's pretty much it. If nothing to erase, we return an iterator, and otherwise we return the next iterator after the erased one. That's how erase for vector works. And this is how erase for flat map things will be working, because it's just a container adapter. So I strongly believe. So then here the complexity is completely the same. If we erase something at the beginning of the container, and we are not cheating, no pre-allocating, no something. If it's literally contiguous container, we again getting the linear performance. So we need to shift all elements. And it's the same as insert. It can invalidate iterator some or all or only just after the container, but it's implementation details and you cannot rely on them when you're doing real code. Now we should consider flat map, and the reason why I decided to talk about flat map separately is here. There are at least two different possibilities how you can implement flat map. The first one is a contiguous container of key value pairs. So you have a vector, and then you have a pair. First element is key, the second is a value. It's fine. But there is another layout. So, and the second layout is two different containers. One container for keys and one container for values. Now, that's a short quiz. Guess what implementation is widely used in the world nowadays? First or second? It's first. And guess which implementation goes to standard? Yes. So that's the point. Is that those implementations are slightly different in terms of performance. And from what I know, there is only one implementation of the second approach now. It's in a private API of the Qt library, and they have their own flat map. They implement it completely as it's done in the standard. So that's two containers. I guess, yeah, I reviewed that particular patch, and it's implemented. Just all interfaces are super consistent with the standard. So they just copy paste in terms of interfaces, which is kind of cool. We have sort of a reference implementation. But in a few slides, I will show some caveats of the second approach. But before, we should see that the possible implementation, we have slightly larger implementation that we had for just map before, for set before. We have now keys, values, we have comparator, and we have separate containers for keys and values. Those are also copied from the standard, I guess, probably even with this capital stuff. And the limitations of those containers are the same as I said before for set. So for iterators and for sequential of this container. Then we have data structure that contains keys and values. We have data members, and we have comparator. Let's move to the most interesting thing. Iterator. So who has ever implemented own iterator? So that's interesting thing, because iterator has some operators to dereference itself and to return mutable reference to the internal data. That's a super good question, since iterators are implementation defined based on the standard. So what should we return if we have two different containers? It's not a question I want to answer here. It's very tricky, and I don't even want to put some current implementations on the slide, because you don't want to see fake pointers, fake references, and some other stuff to implement it. But I have a very simple iterator here, just to show how algorithms are working. So this iterator doesn't contain any things to dereference, to access stuff. I'm cheating again. The iterator contains only a reference to data and the position, which is, of course, since it's naive implementation, not initialized, but it's not important here. So then we can start with implementations, and implementations are a little bit more complicated here. I usually don't like putting wall of code on my slides, and I hope it's not wall of code, but that's the smallest implementation and the densest sparse implementation I could came up with. So we still have lower bound, but we're now using lower bound only on keys. So because, again, we access our data only through the methods, and that means that two containers should be consistent. Or we have completely broken invariant. So if key is found, we check in it, so then we can return the reference to the data packed into our iterator, and then the position, which is just a distance between the begin of the container and what we found. And if nothing found, we return an iterator again, but it's very specific iterator. So with the size of container is a second. So it's kind of improvised end here. So it's longer than the container itself. It means that iterator is kind of points to the end. No questions so far. I don't put any complexities here because all complexities are the same as with set, the same properties. Now we have insert, and for insert, we again need to do search to do lower bound. We are inserting pair of key values, as that might be a good idea. Then first would be key. We're looking for a key. Then we check in whether we can insert or not. Again, we shouldn't insert if the key is already in the container based on the standard reference. So when we insert, we have now insert something to the keys. Then we found a distance of where we inserted things. And then we can insert value after that exactly into the same position. And in iterator, since it's consistent, we just return an iterator with the data and the position. And again, if we cannot insert, we return something that just points to the end. So I guess you could read code. I will publish the slides both in channel and then they will be published. So if you need to revisit it, you can do it later if you don't have time to read right now. And the erase is also super easy here. To short amount of code, I decided to implement erase for iterator, but again, if you need to do it for key, you can invoke find and then invoke this erase, so you can implement one in terms of another. You need to also potentially check the iterator consistency, whether this valid iterator, it's iterator from the same container or something like that. But I just pointed out here. In many cases, you probably don't need to do that. Then you, again, find in an element, erasing it, and do the same for values to keep it consistent. And we are done. Here we can return an iterator with a distance and the data again. That's how those three major functions can be implemented. And the operations complexity now for search, it's logarithmic, binary search, very good. For insert, it's linear in the worst case. And for erase, it's also linear in the worst case because we might need to relocate all of the elements. But you might now see, okay, fine, at least 2 out of 3 operations for flat containers are much worse. So we don't probably want to use them in many cases. But apparently we might want to use it, and on practice, some log n might be faster than another log n, and we should see why. So the main question, what are those containers for? And those 2 containers, why they even exist, they utilize one of probably 2 fundamental properties of physical hardware. The first one, we should talk very briefly about caches. So, and who are familiar with how CPU caches are more or less working, what is cache locality, cache line, and stuff? Oh, okay, good. I don't even need to probably include this section. But anyway, there are many good talks about data access patterns, cache locality, some other stuff. I'm just, there were so many, you can just pick what you want and watch. I'll just say very briefly. Imagine that we have a linked list now, single linked list, forward list from standard library from STL. So, and I want to iterate over this list. That's how this list of 4 elements can be allocated in memory on heap, because each node can be allocated separately. So to process it somehow, CPU needs to fetch it, to read it from the RAM. And to do that, CPU doesn't fetch things by 1 bit or 1 byte, because it's when it's addressing. So it just fetches by chunk. So, and say I want to read the first element. Okay, I fetched this chunk, and in this chunk, there is only 1 element. I want to iterate over, and there is nothing in my cache. I need to go further. I need to fetch another chunk, and there is second element. Good. But I want to go further, and there are nothing. And lucky we, for the third read, we get 2 elements, and we don't need to go to RAM anymore. In contrarily, if we have a vector or sorted vector for iterating, depending on data type and many other things, then can be read all at once. So we need only 1 read instead of potentially 3, 4 reads. Doesn't really matter. We can reduce amount of reading from RAM to CPU cache. The famous table, it's probably published in most of the talk. The original is here. You can go and review with some sort of things for L3 cache. I just put my approximate numbers here. But the point is, if we even compare reading from the slowest cache, like L3, which is 2 times approximately faster than RAM, we can read the numbers here. So that's why it might be important to have data put close to each other for them to be cached. So we can potentially access like approximately 10 times faster when we iterating or processing data. That's the one property of having contiguous container for storing data, which is good. And another property, it's very similar, I would say, and originates or tightly coupled, if you will, from the first one. This is about memory fragmentation. So imagine we now have another object, and this some tree of 5 nodes. Doesn't really matter with this. And all nodes are allocated non-contiguous. I'm adding 1 element, it's allocating here, another here, there, and it's super dense, so spread. And if I can count the memory, there are red segments. It's again huge simplification, but anyway. So in those red segments, if you want to allocate 1 more node, you cannot insert it into those red segments. You cannot utilize those segments. What you can use is a green chunk here. But if we have a contiguous container, we can potentially, like all our pairs or nodes, tightly coupled to each other. It just allocated contiguously. And then on the screen, you can notice that the green chunk is wider. So you can put more elements. That's why it might be important to align your data and to use the contiguous container if you have some certain circumstances for use it, because apparently this stuff, this reducing memory fragmentation might be a bad property for some programs, and I will talk why a little bit later. Very important stuff. So I promised you to show benchmarks. Now we had a chat about fundamental properties. We had a chat how things are implemented. And I want to show you some benchmarks because this presentation won't be full or good enough without it. But before we start with benchmarks, I want to tell you just do not rely on my benchmarks. Do your own benchmarks because they might be different build types. So I would suggest to use release with debug info, but I know that some people trying to benchmark debug builds and then surprised by results. Don't do that. But benchmarking on release and stuff, then you might have your own certain tool chain. You might have different hardware, and especially for embedded, this is important. You might have different use cases, how you use the structure, how often do you insert, remove elements, and so on. You can have different data types because size of data type is also important. Like it's either 3x64 integers or 1x16 integers. That difference is critical. Then data types and the number of elements, of course, because if you want to allocate from time to time 1 million of elements contiguously, that might not work in many cases. So I used my home PC, which is kind of outdated little bit configuration for all tests. Those slides you can also review later if you want. There are RAM timings, CPU stuff, and so on. Very important for some and probably not super important for us now. Then data types. I benchmark 4 data types. That's 16, 32, 64-bit integers and mid-size port. I decided that mid-size port is something like 3x in 64. You can disagree with this or agree, but that's what been my benchmarks. And since I had many benchmarked, many things from 100 to 100,000 elements with a step of multiple by 10, I will not present all of the results, but all images, they just automatically generated by plot here. So if there are some things with scale or fonts, they should be readable. I checked on another protector, but we will see. And we will start with find operation. So is it readable? Oh, I hope it's more or less readable for you guys. So in top here we have what we are benchmarking. There is an elements count, 10. We are find for 10 elements. Here from blue to red, we have 16, 32, 64, and mid-size port. And at top, we have boost flat map, which I should remind implemented as a sequence. It's one container of key value pairs. Here we have stud flat map. It's my own implementation because there are no implementations apparently. And in the bottom, we have standard map. So do you all see it well? Yeah? Okay. So, and the time in nanoseconds for small numbers of elements, that's just a scale, but for large number of elements, that will be logarithmically scaled because otherwise you cannot fit it. You will see. And for find, we can see that it's more or less the same benchmarks. We cannot tell much from it, especially taking into account some deviations from the hardware use cases and so on. But the boost flat map slightly overperform if we use and find. And yeah, you may see that I'm comparing maps, not sets, or it would be completely boring. But in the second case, we jump in from 10 elements to 100,000 elements. And here the situation is a little bit more interesting. So if we use found on 100,000 elements, we can clearly see that stud map is working much, much slower. The scale is now logarithmic stuff. You can just probably estimate amount based on this. And the flat map, we have a flat map of 2 containers. Not surprisingly, it performs faster than the boost flat map, which is much wider, and you can take less elements into the cache at once. So that's why it performs worse. But again, for a large number of elements, I got this benchmark, and it's probably not even noticeable here, but it's just slightly faster than the flat map, the boost flat map. So all data also will be attached, and I probably will attach even all pictures, data, and benchmarks as an archive or GitHub repo. We will see. Now we should move. So far, no questions, surprises, or something. Yeah, okay, that's expected. For insert operation, Some operations you probably shouldn't perform super frequently on flat containers. Here we have 10 elements. And surprisingly, I have this spike. I measured it a lot of times. I used Cage2 benchmarks for benchmarking things, and there are already few iterations by default, but I tried on different machines, and I got this spike here for the flat map, perhaps because my implementation is bad or something, but it's notoriously slower for inserting elements, or because you need to relocate to containers or doing something like that. I can only imagine this. I didn't check profiles reports, to be honest, but for flat map, we can see that it works kind of faster in average than both flat map and stud map. But the situation is slightly different if we insert a large number of elements. So, and that's again scaled, the x-axis. So, and if we insert a lot of elements here into map, so that works fast, super fast. And if we do the same for flat map, for some types, it works a little bit faster for 16-bit int or for 32. But the mid-size port, X3 in 64, it's like comparable for both flat maps. But again, the flat map is proposed for the standard library, kind of performing better even for insert numbers. Then arrays. I am not sure why. Don't ask me, please. But probably Boost flat map, they somehow cheated in implementation or something, or not exactly erase or not relocate. It's just standard Boost thingy with a default container. But it's much, much faster when we are trying to erase, and especially when we are trying to erase it in 64. So it's probably on my system again. But it's much faster than all other stuff. And I suspect if you play with underlying containers, there you might get different results. But here we go. So that's what we have. And if you want to erase large number of elements, again, it's scaled. Obviously, stud map is much faster, so you don't need to relocate this one. But again, flat map from the standard library is better in terms of this point of view of this benchmark than the flat map for Boost. So if we even do many operations, then we can somehow conclude, based on this unreliable data from my personal PC, that flat map can be better in terms of two other inefficient operations. But again, you should do your own benchmarks. And this particular test I added because some people asked me to do, and they said you need to insert iterate over vector and compare it to iterating over map. That's what I'm doing right now. And the results are also very interesting, to be honest. So the iteration, surprisingly pretty much the same or comparable for both flat map and my flat map implementation, and that's slightly slower for map. And if we have a large number of elements, so the iterating over Boost here for the small elements is kind of faster, but for other elements it's comparable. So if you just iterate over things, so you might don't want to really care how your keys and values are allocated either to containers or in a single container. But again, it was benchmarks from my own machine, so do your own. Don't rely on this data. And now we can talk about advantages and disadvantages, flat versus non-flat. So let's start with pros and cons of using standard set or map. I'm combining it here because that's pretty much the same under the hood. So, and at the first line for both first pro and first con, you can see that I put here that it's non-contiguous container. And why it was pros and cons? Because apparently it does utilize this memory thingy, cache, memory fragmentation and stuff. But on the other hand, is a pro because the memory of your system can be in so bad state that you cannot find enough contiguous memory to allocate chunk. And this is an issue. So if your system in this state, that's definitely a con for you. But among pros, there is good complexity. Good complexity is for all three operations. It's very predictable. It's very consistent. It's nice to use it. Then no iterators, so references are invalidated. So it just allocated somewhere on heap. You can access, use it. Very cool. You can even take a node handle if you want. The newest standard. But the cons is, as I said, about non-contiguous stuff. Then memory fragmentation, not good for many systems. So your system might get into the state where it cannot allocate a contiguous chunk by a reason, because your memory is too fragmented and you're not using pools for small objects and something like that, and your app is running for a long time. And potentially, there are more cache misses. I had this table. You can see how many cycles or seconds every cache miss can cost your system. But again, it might not be an issue for you if you're not running some high-performance applications or games or something like that. So if it's a desktop software, for some reasons written in C++, then you can just mostly ignore this negative part. And now we are talking about flat stuff. So, and again, first pro and first con, this is a contiguous container, right? So you might, again, have not enough memory to allocate the contiguous chunk. It's mostly will be contiguous container, to be honest. And it's a good stuff that you can avoid memory fragmentation just by allocating those chunks. This has better cache locality, for sure. The fast iterating and searching, we saw it even in our benchmarks, and then from the implementation. But then it's possible to choose a different underlying container. Very cool stuff, especially if you use it for small caches or something. So you can take boost small vector or things that pre-allocated elements even on stack if you want, and then utilize this. You just can create it at once and use. Very good and very fast. So, and as a cons, 2 major operations, insert and erase, slow. And insert operation can invalidate iterators as well as erase can. And usage advices. I partially, I guess, touched many of these things. Have a good time? Yeah, we are. So you should use flat containers if you have relatively small count of items. So it might be 10, 100, 1000, even more. It depends on the element size. So if it's 16 ints, you can put more, or if you have specific memory in your embedded thing, specific traits, you can again put more. It depends, but it's recommended that you have relatively small number of elements for this container. Then relatively small elements themselves. So if it doesn't perform well, if even it's like mid-size pod in general, but it can be good. It depends on how you utilize the properties of those structures. Then there are no many inserts and erases operations should be performed on these containers. The probably best usage scenario that you can create it at once. Doesn't matter how, but you create it once and then only use for either iterating or for searching elements. As I mentioned, that's very good if it's like a small cache. I use it for small caches, for stuff like that, or even kind of embedded thingy, but yeah, that's the best case. So it reduces the memory overhead and fragmentation. Why I separated the memory overhead? Remember my implementation, naive implementation of the tree node? It has more fields. it has a field for color, and it has 2 pointer fields for subtrees, and then it has, of course, key value stuff. So the memory overhead, there are some benchmarks from Google, I believe, and they show that the memory overhead of flat containers is much less than especially if you use more of those containers in your program than if you use standard maps or sets. It uses memory fragmentation because it's most likely will be contiguous container. It's one chunk of memory allocated a chance. And the last bullet, so I also mentioned that you can allocate or pre-allocate or use different containers. Just utilize this property since it's container adapters. Standard vector is good. It's a default container for pretty much everything. You don't know which container to choose, go for vector probably. But you can play with this. Just experiment what better suits your needs in the app. And with this, I don't have, I believe, anything else to share with you guys. Don't want to hold you before the lunch. Thank you for attending. Yeah. Yeah, shoot. That's a good question. I don't really know, but we can probably check the reference and standard. But since it should be, why not? I mean, if the underlying container is able to use it, many methods in interface are also marked as a const export from what I remember, so it should be possible theoretically, but I cannot give you 100% guarantee. So, any other questions? But yeah, if not, thank you again. We're done.